Thank you. This is an experimental talk. I'm going to be talking today about quasar data. It's a project that began, as John Barrow said, over a decade ago. It's taken a lot of people. This is not merely my work, but quite a few PhD students, and indeed undergraduates as well, actually, have been involved in this project. It involves a great deal of data, an enormous number of nights on the telescopes. I'll talk quite a lot about the data shortly. And it's obviously trying to connect some of the ideas that we've heard today to real observations. And I suppose what I want to convince you of by at least the end of my second talk is that we really can make extremely high precision measurements now at high redshift and test some of the interesting ideas that we've heard about in the previous two John talks. This is the third John talk of the day. John Barrow went through some of the history of the subject, and Paul Dirac was obviously very important. Back in 1938 he came up with the large numbers hypothesis, which is an important, historically important piece of work in this field. The little video that's showing there is a video of Dirac when he visited Australia in 1975, and he gave a series of lectures in Australia and New Zealand, 4 of them at my university. There's only a little snippet there, but that's actually Dirac giving his one of the 4 lectures on the large numbers hypothesis. And he wrote John has already explained the idea, but very, very simply, Dirac was interested in the fact that 2 ratios, one relating to a macroscopic scale, one relating to a microscopic scale, both huge numbers, around about 10 to the 39, were of the same order of magnitude, and he regarded this as more than a coincidence and hinting at the possibility that there could be some new law of nature in it. And since in that ratio, in the handwritten box there, on one side, H rather is a varying quantity, then one might expect that one of the numbers in the second ratio might also vary. And so he spent quite a lot of time, in fact a whole hour, talking about this in his lecture in Sydney, and a book was produced, just for interest, of those lectures in 1976, something like that, where he devotes a large number of pages to this topic. He kindly donated the royalties of the book to my university to establish a Dirac medal and a Dirac banquet every couple of years, and that continues to this day. Unfortunately, the book isn't exactly a bestseller. And so the total annual profit is something like about £5. But after this conference, I'm sure there's going to be a boost in the revenue, and the Dirac banquet might not necessarily next time be a cheese sandwich. We've heard a lot of things. I've just got a couple of slides of interest. It's interesting to recall that if we only had a 4% change in the fine structure constant, which is what I'm going to be talking about, then it would have shut down heavy element production in stars, more or less, at least to the extent that life as we know it could not have been produced. And there are so many other examples of fine-tuning. It's an interesting concept, but I promise I won't mention the A word here. This is a list of the things that we can actually check with astronomical data. Of course, as you know, we focus on dimensionless quantities, because those are the things that we can actually measure meaningfully. Things like the fine structure constant, which is the one I'm going to be talking about in detail. Of course, the ratio of the electron to proton mass has also been studied in a lot of detail, and there's now some very high precision constraints on variation of that quantity at redshift out to 3 and 4. Other quantities, and I think I'm going to be focusing in this talk on optical spectroscopy of quasars. They constrain the fine structure constant, but there are some new observations using radio astronomy which constrain combinations of constants, and I think this is possibly the future of the subject because the data is becoming so good, even though it's in very sparse supply. The one advantage of the optical data that I'm going to talk about is that there's plenty of it, and in fact, even though we've got a very large sample of measurements now, by far the largest that's been done, around about 300 measurements. We're going to be able to quadruple that in the next, I hope, 3 or 4 years. And so we will have some definitive answers, I think, perhaps not definitive, but some very clear statements to make about some of the controversial measurement I'll show you during this talk. The data come from 2 telescopes, the Keck Observatory in Hawaii. The cost, if you're interested in such things, is in the top right-hand corner. There's a very, on this telescope and on the VLT in Chile, there are 2 exquisitely good shell spectrographs which can make such high precision measurements of spectral features at high redshift, that when we started this work, it became very quickly apparent that we were able to measure spectral features with data from these instruments far better than had ever been done on Earth. And this was a serious problem because it meant it spoilt our precision of the constraints. And so the very first thing that we had to do over a decade ago was to convince a bunch of laboratory astrophysicists that they needed to go back to their laboratory instruments and remeasure many of the transitions that had been that were now being observed routinely in the high redshift universe. The real meat of what I do and my team does is actually take data like the data sitting at the top. These are a shell spectra of distant objects where the individual spectral orders are split up to fit onto several CCDs in a kind of compact format like that, so that it becomes practical to cover almost all of the optical waveband. The black lines that you see there are absorption lines in gas, and the general principle here is, in this cartoon, is you have a distant quasar there and a long line of sight, perhaps covering up to 10 billion light years to the background quasar that necessarily intersects gas of one sort or another. In the cartoon there's a galaxy which falls quite close to the line of sight and causes considerable absorption, and that's what we're interested in. That gives us a wonderful opportunity to study at high precision the physics in the gas cloud at the time that the light passed through it. So that thing that's simulated in the spectrum on the bottom is a damp Lyman alpha line, and associated with that very strong hydrogen absorption you have a lot of other heavy elements, and some of them are illustrated there: singly ionized silicon, singly ionized carbon, triply ionized silicon and carbon, oxygen, nickel, zinc, chromium, and all sorts of interesting transitions that we can then go away and measure with enormous precision, but we must have the high quality optical data, laboratory data to compare that with, otherwise we're lost, we can't do anything at all. The whole principle here, of course, is that we are comparing the spectra that we see from these distant gas clouds with the same spectra from the laboratory to see if physics has changed. I wanted to, near the beginning, show you some real data. This is some data that we're working on right at the moment. It's not published yet, but this is a spectrum of a gas cloud at a redshift of 3.25. This particular spectrum is the result of quite a few nights on both the Keck telescope and the VLT. And the data's been combined together like that just for illustrative purposes. The wiggles of the absorption lines of the different components of gas at different velocities along the line of sight. It's a complicated pattern that has to be modelled accurately if you want to pull out physical parameters. And this procedure is very tricky. As I go on, you're going to hear how tricky it is, but I don't want to convince you that it's so tricky that you can't pull out accurate physical parameters. We can. We've been doing this now for quite a few years, and I think that we have a very good handle on the errors, both random and systematic. So I'll talk about those in some detail. So I think we understand not all of the errors, certainly, but quite a few of them. But also, importantly, the models that get fitted to data like this are complicated. They can have not 19, but up to 300 or so free parameters. And the free parameters are actually, in many cases, connected to one another. They're not independent parameters. And it's this that one has to pay great attention to in order to make accurate measurements. And this is difficult, and I think this is why we're still really at the beginning of this subject. I think we're close to the beginning of the field, but in 10 years from now, we'll have some, I think, incredibly high precision measurements. This particular spectrum at the top is hydrogen Lyman alpha, next row is Lyman beta. As a matter of interest, the red dashed lines there illustrate neutral hydrogen, and the dashed blue lines are actually clear detections of deuterium at high redshift. Deuterium that was formed in the Big Bang nucleosynthesis. The heavy element abundances, although there are heavy elements in this gas cloud, are very low. It's probably about 1/100th of the solar abundances, so not that much processing of this gas has gone on. And what that means is that the abundance of deuterium is the primordial abundance, and that allows us to make a nice measurement of that for a different topic. But in addition to that, we can also measure all of these heavy element transitions, and there's just some of them illustrated there. But what you can see there in the lower panels in particular is the complex velocity structure in the gas, and that's what we've got to model very carefully if we want to be able to measure the fine structure constant. Now I want to go through some very elementary things. They are elementary, but they're actually crucial to producing reliable models such as you see there. So the data in that case actually are so good that it's difficult to distinguish between the data and the model. You can see the normalized residuals in the top band with the 1 sigma error bars as horizontal red lines. It's just that the data is so good you can't quite tell that there's noise in the data. Now, we use nonlinear least squares for this, standard nonlinear least squares. There's nothing particularly fancy about that. It's Gauss-Newton unconstrained optimization used in many areas of experimental physics, obviously. But the thing that one has to get right in measurements like this is the first guesses, because we don't have a defined model. We have to look at this data and see all of these wiggles, see all of these absorption lines, and decide where there is a gas cloud. Where is there a dip? That may seem trivial, but you might also then think, well, what happens if you get your model wrong in the sense that you have the wrong number of free parameters? What does that mean for measuring the fine structure constant? And the interesting thing is, because the answer to that question is not at all obvious, but we've been doing some work recently with genetic algorithms. This particular fit that you can see up there was done by hand. Somebody sitting down, looking at the data, deciding where the dips are, putting in a Voigt profile, building the complexity of the system up, hours and hours and hours until you get a really good model, looking at chi-squared, looking at other goodness of fit statistics. But on the other hand, you can't take the fact away that somebody had to sit down and make a decision about the model that's being fitted to the data. And this is crucial to the output. We've just been going through, for the last couple of years, a study using genetic algorithms where we try essentially all possible, within reason, not an infinite number obviously, but all possible configurations of a first guess model. And then we look to see how the sensitivity of measurements is impacted on by those first guesses, looking at hundreds of thousands of first guesses. And I haven't got any slides to talk about this, and we're writing a paper about it at the moment, but the interesting result of that is that there turns out to be quite a good stability to the input guesses. And that's why I said with some confidence earlier that I think we have a good understanding of many of the errors in this procedure. So there's an interesting stability in the final measurement of the fine structure constant that you get out of data like this, not very sensitive to the first guesses. Quite a little bit surprisingly, perhaps. Just some basics. One absorption line, and you saw many in the data, are described by 3 parameters. There's a width, which is determined by the temperature of the gas, the internal velocity dispersion of the atoms. There's a depth, which is determined by the column density, the total number of atoms along the line of sight. And then there's a position of the line, which is determined, of course, by the expansion of the universe, by the redshift, but also by the rest wavelength of the transition. So the observed wavelength is just 1 plus z. Z is the redshift times the rest wavelength. So there are 3 cloud parameters for a single absorption line. This is now, I want to build this up slowly to explain why it gets a little bit complicated. Now, if you have parameters describing 2 or more absorption lines from the same species, such as an alkali doublet like Magnesium 2, which has 2 transitions, 2796 and 2803 angstroms, well, it's the same gas, and therefore you've still only got 3 parameters describing those 2 absorption lines. So still easy. You've got 3 cloud parameters, no assumptions. There are more physics parameters, of course, because you've got 2 lines, so you've got 2 rest wavelengths, but still only 3 free parameters to fit to the data. Now, suppose instead you have 2 species, not just one, so magnesium and iron, and those are species that are commonly seen at high redshift, and species that we can measure very well, they're quite strong. Well, now, if you have no assumptions whatsoever about these species, you've got 6 parameters, 3 for each. You've got the column density for each, you've got the line width or velocity dispersion parameter for each, and you've got the redshift of the line independently if you make no assumptions. 6 parameters. But you can be a little bit clever about it, because you know that the measured line width is a quadrature addition of 2 things. If the gas were thermally broadened, it's very simple, because the line width is just inversely proportional to the square of the atomic mass. KT is a half mv squared. But if the gas is not just thermally broadened, but is broadened by turbulent mechanisms as well, then there's another term that you have to add in quadrature. That's the top line. Now, there the temperature, the T is the cloud temperature, which is not easy to measure very well, unfortunately. M is the atomic mass, and obviously know that. So if we understand the relationship between the 2 species, between, in this case, in this example, magnesium iron, then there's going to be some boundaries, because if you have completely thermally broadened gas, in other words, the bulk term is negligible, then it's easy, because you've just got that the ratio of the square root of the atomic masses is going to give you the ratio of the line widths. Very straightforward, and in a numerical method you can code that in to reduce the number of free parameters. That's the point of what I'm saying. On the other hand, if the thermal component is negligible and the broadening of the absorption line is caused mostly by bulk motions, that's the other extreme, and the line width of the 2 species is going to be identical. Now, these things you can code in, but you must do this properly in order to draw out the parameters of interest. So you can reduce the number of cloud parameters if you've got 2 absorption lines from different species appropriately down now, instead of 6, down to 4 parameters. And there are now assumptions, and the assumptions are that this gas, the magnesium and the iron, arise in exactly the same physical location. There's no segregation in any sense of these species, no physical or velocity segregation of these species. There are assumptions, and the assumptions we have to think about and justify. I may come back to that. Here's some more data just to give you an idea of what actual data looks like. This is a kind of intermediate redshift data that we measure. Magnesium and iron transitions. Some of them are very weak, some of them are stronger. Here's another one where the line's saturated. So for example, top left, there's an iron transition at 2383. The blue tick marks illustrate all of the different individual clouds of gas that make up that model. All of that has to be modeled very, very carefully using the entire set of data to get the velocity structure as right as you possibly can, but not unambiguously so. But remember what I said about the genetic algorithm approach, which seems to show that the output is rather stable to the guesses. But you can still build up you can see the normalized residuals there, you can still build up very good models to match the data. It's just that they're not. You could find equally good statistical fits using other models. Now, up to about 1998, people were using something called the Alkali doublet method to constrain the fine structure constant using quasar spectroscopy. there are some fairly commonly observed transitions, triply ionized carbon and silicon and singly ionized magnesium, all seen routinely in quasar spectra. The total number of quasars that have been observed on those two telescopes to date is of order 1,000, something like that, just approximately, maybe a little bit less. The total number of quasars known about comes mostly from the Sloan Digital Sky Survey and is more like 100,000. But obtaining the data itself is quite hard. It takes a few nights on an 8-meter telescope to get really good quality spectrum of a high redshift quasar. Now, the alkali doublet method that was used until the many multiplet method was invented is summarized at the bottom. We were measuring transitions from the same ground state up to an excited state with the alkali doublet transition. So there were simple transitions, 2s½ to 2p3 halves, 2s½ to 2p1 half, and the relationship that you get out of that is that a fractional change in the fine structure constant, delta alpha over alpha, is the change in the wavelength separation, delta lambda, divided by 2 delta lambda. So that's the change in the wavelength separation due to a change of delta alpha in the fine structure constant. So it's quite a straightforward and a very direct method. If you've got alkali doublets, carbon 4 and silicon 4, you can easily apply that equation on the bottom right in the yellow box, and you can get a constraint on the fine structure constant. But it turns out not to be all that precise doing it like that. And the reason is here, that if you have a change in the fine structure constant, then the electron feels that change most sensitively in its ground state, if you want to think of it in classical terms, when it is closer to the nucleus. And therefore, but if you look at the top two diagrams there, you can see that the biggest change for a 5% change in alpha is easily in the ground state rather than in the excited states. And so by using an alkali doublet where the measurements are made relative to the same ground state, you simply don't benefit from the potential precision. And so for that reason, we started using, about 10 years ago, all the different species simultaneously to make these measurements. But as I've said, we encountered several problems. Now, what's interesting is that when you work out the response of these transitions to a change in alpha, the response is quite complicated of the different energy levels. And that's not intuitive, but it's due to the different orbital configurations and needs to be calculated using many-body Hartree-Fock theory, which was also begun about 10 years or so ago, and those calculations still being done, both to refine them to make them more accurate, but also to repeat calculations for new species that are being measured. Not that many now, but there are still a few calculations left to be done. So there are some advantages then of using many multiplets, not just the alkali doublet method. And the first thing is that you then take into account the relative shift for the ground state, and that gives you, interestingly, an order of magnitude precision jump. That's the first advantage of the many multiplet method, about an order of magnitude precision jump, just because of the bigger change to the bigger sensitivity to a change in the ground state. The other advantage is you're not just stuck with two lines. So you've got, rather than just an alkali doublet, you can have any number of transitions, and anybody who's looked in any detail at a high redshift quasar spectrum will realize that they are very rich indeed. There are all sorts of species detected. Titanium, nickel, zinc and chromium are quite sensitive. The higher mass species tend to be quite sensitive to a change in alpha. And fortunately, the low mass species, as John Barrow pointed out earlier, magnesium and silicon, for example, are really not interested in what happens to alpha. They're just solid. And that's good, because we have essentially a set of anchor transitions to make measurements with respect to those of the more sensitive transitions. So the second advantage of the many multiplet method is that we can include many species. You can therefore get very good statistics from lots of different atomic species, but also all of the different velocity components in the gas. As I said earlier, some of the models have several hundred parameters, and those free parameters correspond to a large number of different gas clouds. And also interestingly, as I'll show you in a little cartoon in a second, the opposite sign of the shifts for a given change in the fine structure constant helps to remove systematics. Systematics probably plague these observations. I'll talk about that a little bit more. But by having species which shift in different directions, it becomes much harder to have a simple systematic in the data, a simple wavelength calibration systematic in the data, a stretching of a spectrum, a shrinking of a spectrum, if you've got things shifting in opposite directions. So let me just, there's the cartoon that John showed earlier, and you can see the silicon-2 line on the left at a rest wavelength of near 1500 angstroms, and the magnesium lines up at 2800 angstroms. Even for huge changes in alpha don't shift, whereas things like Fe2 drift quite substantially towards higher wavelength as delta alpha over alpha, alpha naught minus alpha z divided by alpha z, the laboratory value minus the value at some redshift z divided by alpha naught, I think I said it wrong the first time, changes quite substantially. You can parameterize that shift in those two equations. So the frequency of some transition seen at high redshift is the laboratory frequency plus a delta omega, and the delta omega is expressed in terms of a sensitivity coefficient Q and alpha z and alpha naught. Alpha z, the value of the fine structure constant in the gas cloud at the time the light passed through it, alpha naught, the value on Earth. Q are the coefficients that have to be calculated, and the definition of delta alpha over alpha is given below. Parameterized in that way is quite useful because it's hard to calculate Q very accurately. I think probably the best values are known to within about 5%, perhaps a little better in some cases, and some of them as bad as 10%. But even if there are fairly substantial uncertainties in Q, we are not going to emulate a change in alpha through uncertainties in Q. So this is just showing you what happens to the lines as you cycle through different values of delta alpha over alpha. It pauses at 0, so those are the terrestrial values, and you get quite a different pattern. It's, for a given value of delta, I'll run it once more, delta alpha over alpha. So you can see the magnesium staying still, you can see the silicon-2 staying still, but the zinc and the iron very sensitive, and the chromium is going in an opposite direction to the iron. So it's hard to emulate a change like that with a simple systematic distortion in a spectrum. Also bearing in mind that the gas clouds that are being observed are not at the same redshift. They're all at different redshifts, and therefore the transitions fall at different observed wavelengths. It may be possible to emulate it, maybe nature's cruel to us, and maybe the results that I'm going to show you are due to systematics. It's possible, but it would be a rather cruel act of nature if that's the case. The first substantial sample that was published was quite a while ago now, and it came from the Keck telescope, and this is the sample. So on the y-axis there is a fractional change in alpha against redshift. Each of those points is not an individual measurement. Each of those points represents 10 to 15 measurements put together. The horizontal dotted line clearly is at 0. That's what we would have expected to see if alpha were not changing. And what you see is that, at least in those data from the Keck telescope, the points sit systematically below 0. Interestingly, even as we approach low redshift, the points don't go back to 0. They are staying low. I'll come back to that point and I'll explain it. We understand this now. Here's another way of looking at the data. So this is the Keck data alone. Now I'm going to rotate this, I hope, and you'll be able to see the more negative points in red and the more positive points in green, just so you get a visual idea of the data. You may or may not, I don't know, think that there are more red points over on the right and that there appears to be some kind of spatial asymmetry in those data points. If you add the VLT data to that sample now, total of about 300 individual measurements in the data, then you may or may not think that you can see some kind of hemispherical asymmetry in those data. Once more. So redshift is the axis out from the center in this case. After having made the measurements with the Keck telescope, the obvious next thing to do was to go to a different telescope, different instrument, different software, different detectors, and see what we found. So looking in the middle panel first, that's the same plot that I already showed you for the Keck data, and the lower panel then is what we got for completely different measurements from the VLT. And so what you see in the lower panel is that as you move towards high redshift, the points seem to sit not very significantly, but perhaps systematically above 0, and then below a redshift of about 1.5 or so, they seem to be consistent with 0. Probably unlike the Keck spectra, where they seem to sit systematically low at high redshift, but also systematically low at low redshift, which seems to be thoroughly inconsistent. I'll try and explain this. I think we understand it. When you put all the data together, you get the top plot, where the data seem to scatter quite a lot about 0, but to be largely consistent with 0. Well, you might think, once you've seen the top plot, you would automatically assume that there are systematic effects in the data, and you might then ask me, why did I not go away and do something useful with my life? And it is a good question, which I won't attempt to answer. But we didn't do that, so we decided we'd look a little bit more carefully at the data. There's some numbers at the bottom. For the Keck data, just taking the points above a redshift of 1.8, minus, and using a weighted average, and trying to take into account systematics in a way that I'm happy to talk about if somebody wants to ask questions afterwards, but I won't go into that yet, but trying to take systematics into account as well as the ordinary numerical uncertainties that came out of the fitting process, minus 0.74 plus minus 0.17 times 10 to the minus 5. So these are very precise measurements. But the VLT in a different hemisphere, plus 0.61 plus minus 0.2 times 10 to the minus 5. So marginally significant departures from 0 in both cases, and clearly inconsistent with each other. So that's just showing you the combined sample again. That's what it looks like in a three-dimensional plot. There's a hint of a hemispherical asymmetry. If you simulate spectra, this is how it would look in an ideal world. That's a little bit clearer. So we've played around with simulations. We've played around with in doing a spatial analysis of these data, one has to take into account carefully the fact that we don't have uniform sky coverage. And so we take that into account using a Monte Carlo bootstrap method, and we believe that that's dealt with properly. Interestingly, if you split the data up into two redshift bins, so this is the low redshift data, which you might want to have a look at. combined from both samples, but the low redshift end of the data. It's interesting to compare that to the high redshift data. Where there seems to be, at least visually, more evidence for the hemispherical asymmetry. Consistent with what you see in the summed plots, where clearly the two samples have just been divided into two, one for each telescope. So just to summarize, so you can see what I'm saying. If we have a pattern of lines that we see in the laboratory on Earth in the middle panel, then if there's no change in alpha, that same pattern just shifts up. It would be expanded because of the expansion of the redshift. It would maintain, nevertheless, its same relative spacing. The ratio of the wavelengths would be constant. With Keck, what we seem to be finding is that the lines that are low mass don't change, but the ones that are of high mass do change. And so in the top panel, you can see a pair of lines which move together, but in the bottom panel for VLT, although the anchor lines don't change, we get the opposite change for compared to the Keck telescope. That's what, of course, this is exaggerating it, and I'll come to statistical significance in a minute. If you put the data together and you just fit a really simple model to the data, so just a simple cosine model with an amplitude and a constant to take into account the fact that there, visual at least, appears to be a monopole plus a dipole term, you get a plot like that. So that's now the data points are displayed as on the x-axis as values plotted against, measured with respect to a preferred direction on the sky, which has been solved for with a simple dipole model. And then the vertical axis is just a fractional change in the fine structure constant. And that's what it looks like. So we would expect them all to be along zero for no change. The dipole model, the C term in that equation up there, is illustrated by the horizontal dotted line, and you can see it quite clearly. There is a dipole. That's a bit of a concern. It doesn't really make any physical sense. But it is now completely understood, which I'll come on to explain in a second. If you take the Keck and the VLT dipoles independently and you solve for a position on the sky, so that's the blue and the green contours in that plot, they do seem to agree pretty well on the sky, and then you get a combined contour, which is the red one there. If you the probability of those matching up is not particularly small. Given the data, the probability of getting the alignment that's seen is only about 6%. If you split the two samples up, so you keep the telescope data together, but you split them up into low and high redshift, then you get the contours shown on that diagram. So for Z greater than 1.6, you get the blue contour, Z less than 1.6, the bigger green contour, which I think is consistent with the visual impression that you get from the rotating 3D data, where there was really no indication of anything happening for the low redshift end. And then the combined sample now losing the redshift information is the red contour. If you take the data and say, well, let's just suppose for a moment that there is a preferred direction in the universe, then we could imagine collapsing the data points onto a single axis through the universe. Just, in other words, just taking a value for, in this case, the x-axis as being r cos theta, where theta is the angle between the point that's being measured and the preferred direction on the sky, and then plot that against delta alpha over alpha, and that's what that plot is. So there are negative distances here because this is looking in two now opposing directions on the sky. So we're at zero, positive in one direction, negative in another direction. And you kind of get a linear trend out to approaching 10 billion light years. So the data go a long way, and it looks as if, although the error bars are large, that it's just really a linear trend out for as far as you can see. You might ask the question, well, could it be the case that you've just got a few rogue points, bad measurements in the data? You can check that by just iteratively, you can check it in a number of ways, but one way that we've looked at that is to iteratively discard the most deviant point, one point at a time, and then solve again for the statistical significance of the dipole, and that's what that plot represents. So on the horizontal axis, the fraction of the data trimmed is plotted, and then that's the statistical significance of the result on the vertical axis in units of sigma. Now, it looks pretty significant at 0 trim, but that's because we haven't attempted in those numbers to correct for systematic effects. The scatter in the data is larger than is expected entirely on the basis of their numerical error bars from the fitting process. We correct for that in a particular way by increasing the error bars in the same way that I believe is commonly done in particle physics. So we end up with a rather conservative estimate of the significance. But if you don't do that, then you get these numbers. It drops from something like 6 sigma to 3 sigma only after you've thrown away about 50% of the data. So, in other words, it does not appear to be the case that there are a small number of rogue data points, highly significant rogue data points, which are explaining the result. Here's a very nasty systematic which we do expect to be in the data, and we've looked at this in a lot of detail. When you go to a telescope and you have your spectrograph, you've got a slit that you have to put the quasar down. You have to position the quasar in the slit, in the center of the slit to make the measurement. That comes down to the skill of the telescope operator, the combined skill of the telescope operator and the astronomer who does the observations. But you could have systematic drifts throughout the night due to problems with the telescope mechanics or some other problem. And so you could end up with an offset at some point in the observations, and the quasar is not quite sitting in the center of the slit. Well, that will shift a spectrum. That at least, even if it doesn't emulate a complex change of patterns, it will certainly shift a spectrum. And so you have to go back to each and every individual quasar exposure and do the best you can to see whether this effect has been present, or even just guess whether it could have been present if, for example, a given quasar has been observed in multiple observing runs or in multiple exposures or even in successive exposures, and for whatever reason the telescope dome was closed because of bad weather or cloud, or somebody went off to observe another object. There's a lot of complicated observing details in this. So you have to, if that has happened, allow for those shifts by introducing yet more free parameters to allow for shifts between individual exposures. And we actually do that. It's a pain. I mean, doing work like that is so detailed and time-consuming. That's why, you know, in 2014 we've only still got 300 of these measurements. But we do that. In the worst-case scenario, you can just throw away all the measurements that you think might have such an effect in. And so we did identify 124, which is, you know, over a third of the data, and we played around with the statistical significance of just removing those spectra. The signal, of course, drops in significance, but you still end up having the same general effect, an apparent spatial dipole in the value of the fine structure constant. There's some, I don't want to go through a whole table of numbers, but we've looked at this in some detail to see how it works. We can, of course, we can reduce the statistical significance down to almost 2 sigma if we throw enough of the data points away, and we're left then with a not a significant result. Where are we with this so far? There are some interesting internal consistencies here. We don't know that we've got a spatial variation in alpha. Of course we don't know. It would be very nice if we did. The data are suggestive. That's how I would put it, and strongly motivate an even more careful and a far more extensive study. That's how I feel about it. There's some interesting consistencies here, which I think, if this turns out to be just due to systematics, will be very irritating, because there's a number of them. First of all, the Keck and the VLT dipole sky directions, they do agree. Different telescopes, different instruments, different software, different data reduction programs, different observers, different everything. Same atomic data, but the atomic data are not causing these problems. The atomic data are now very good. Secondly, the high and the low redshift data sets agree quite well. And the reason that that's interesting is that the transitions are, of course, shifted from their ultraviolet wavelengths up into the optical part of the spectrum. And at low redshift, we're using completely different atomic transitions, typically iron and magnesium transitions at low redshift, whereas at high redshift, the iron and the magnesium has been shifted out into the infrared, and we are obliged then to use different transitions, and we end up using nickel and chromium and zinc and silicon and other things. Different atomic transitions. So it's interesting, given that if it's a systematic, that systematic has somehow managed to ignore the fact that you're using totally different atomic transitions. Third interesting, if you like, coincidence or a point of apparent robustness is that if you iteratively trim the data, it does suggest that this signal is present in most of the data set, at least half the data set. Now, I want to begin talking about the monopole, because the monopole is something that seems to be just wrong. It doesn't make any sense. If you remember what I said about half an hour ago, a monopole signal seems to be present in the data from one telescope, but not the other. That really doesn't make any sense. What's causing it? Now, one of the transitions that we use routinely at low redshift particularly is magnesium. And magnesium has an interesting isotopic structure. Being low mass, the isotopes are fairly well separated, and that's the schematic of how the isotopes look for terrestrial relative abundances. 79%, 10%, 11% for magnesium 24, 25, and 26. Now, of course, we've measured the isotopic abundances very well in samples and laboratories on Earth, but we have not measured those isotopic abundances in the early universe. We don't know what they are. And so the measurements that have been carried out that I've just described have been made assuming terrestrial isotopic abundances, and that's a problem. It's a problem which we want to solve. Now, we have solved that. So the analysis here is also quite complicated, and I'll just say a few words about it. The 24 is clearly the strongest component in the isotopic structure, and then 25 and 26, as I said, at I think 10 and 11%. The width, the separation between the isotopes is way below the instrumental resolution. We can't resolve those isotopes in quasar data. It's not just below the instrumental resolution, it's also below the natural line width of the lines that we're looking at. So we've got no chance of ever, basically, of reliably measuring independently all of those structures that you see in that transition. But so for that reason, we didn't attempt it. We could attempt it, but I just didn't think it was going to work. So we did a trick. We introduced more free parameters into the data, but not individually 24, 25, and 26. We allowed 25 and 26 to scale together as a free parameter and 24 to scale independently. That's motivated by calculations of isotopic production in stellar nucleosynthesis. It's not a perfect assumption, it's a reasonable assumption. The various processes, which I may go into in the next talk or in the last couple of minutes, that produce the heavy isotopes are similar for the way in which the high redshift universe is expected to be enriched. So we scaled the 25 and 26 together, but kept those independent of the 24. We then resolved all 300 cases, individual measurements for alpha, simultaneously with alpha as a free parameter and the ratio of those heavy and light isotopes. So it's a reasonably complicated calculation. But what's interesting, if you do that, you then can solve for the abundance of 24. And that's the answer for the data, for all of the data that exists at the moment, that quite clearly the isotopic abundances in the gas that we're looking at are not terrestrial. It turns out, I won't go into the details in this talk, but it turns out that the value that you see, around about 50% for magnesium-24, is exactly what you expect if enrichment is done by massive stars of the sort that we expect to have done the enrichment in these gas clouds on the basis of other independent observations, notably ratios of abundances of other species. It actually works quite well. It's what you expect. Nothing surprising here at all. But now if you then use those isotopic abundances that we've solved for and go back, fit for alpha. So there's now the same curve that I showed you before, so it hasn't been done here. If you now solve for the isotopic abundances, introduce them as free parameters, interestingly, that's what happens to the data. So the monopole simply vanishes. The horizontal dotted line now is not significantly different from 0, and I'll flash between those two. The monopole arguably tightens up a little bit. The statistical significance goes up from about only 4.2 to 4.3 sigma. That's where we are. It's not hugely significant. And there's some details there and some numbers that I look at. So I think this then counts as another little tick on that box of apparent robustness, if you like, that I had. So the fourth point is that the monopole vanishes once you put in the non-terrestrial magnesium isotopes. Now, that didn't have to work out that way. If this is purely a fluke result, it could have gone the other way. There would be no reason why it would not. So it's another little piece of evidence that is suggestive that this could be real, and that's the only way I put this at the moment, that it's just a suggestive result. I want to say one other thing. One question that you might ask is that, well, all right, so if you've got a preferred direction in the universe with the fine structure constant, what else is there? What other type of astronomical observations are there that might suggest anything vaguely similar? Well, I took this plot out of the paper that's referred to below, and I just added one other point. So these people pointed out these coincidences first. But there are various measurements that people have made looking for asymmetries, anisotropies rather. There's the new, well actually it's down there as the WMAP measurement, but the Planck data also show the same thing, that there is a residual hemispherical asymmetry in the CMB data once you've removed the standard CMB dipole, which is apparently not consistent with an isotropic universe. The great attractor that Donald Linda Bell is in the audience as the discoverer of sits there with the star, the alpha dipole, and I promise we never looked at this before we measured the dipole in alpha. Wouldn't have dreamt of it. It didn't even occur to me actually. We didn't expect to find a dipole. The alpha dipole sits there in the blue contour. People have looked at anisotropies in the supernovae 1A data, and there's been various papers on that. I think the most recent measurement sits there with the green contour. Bulk flow measurements as determined by galaxy survey data and also by Sunyaev-Zeldovich measurements. Controversial. None of these are individually statistically significant, but Sunyaev-Zeldovich measurements as well as bulk flow measurements a little bit offset, but generally the same direction. The statistical significance of those alignments has been calculated in that paper listed below, and it's reasonably significant, but to emphasize, individually, none of those, including alpha, is itself highly significant. Alpha is at about 4 sigma. I think actually the CMB hemispherical asymmetry is rather significant, and the great attractor, of course, is significant, but the supernovae dipole and the bulk flow dipole are, well, I think at least debatable, controversial. So look, that's as far as I wanted to go today. It's an interesting situation that we have. I think that for this optical quasar data, we can improve this sample on a timescale of 2 to 3 years if we work really hard by a factor of about 3. So at least what we will know is whether it's a 4 sigma or a 0 sigma or a 7 or 8 sigma result. We will know that, I think, in 2 or 3 years. The data, in fact, already exist. We don't have to go back to telescope to do these measurements. The data have been collected routinely for a number of different types of reasons, projects, and they're sitting in the telescope archives. We're working right now. I've got a team of people who've been working over the Southern Hemisphere summer, extracting data from the archives and reducing them, and we'll be able to, I think, at least triple this sample and see whether the statistical significance will hold up. At the same time, there are other people doing interesting work on trying to measure wavelength distortions in the sort of instruments that have been used to make these measurements, and wavelength distortions are present. Jonathan Whitmore at Swinburne has found some interesting non-linear wavelength distortions over the entire optical range, and maybe we can find 2 different wavelength distortions applied, one to the Keck and a different one to the VLT, which will ultimately make the result go away. That's yet to be determined. But we're in a difficult position because there is no way of really independently determining what those distortions are for the quasar data. The way that this work is being done is to make observations, and in fact Paolo Malaro is here, who I think initiated this type of work, making observations of asteroids, comparing the asteroid spectra to high precision template spectra and looking for shifts in little wavelength bins all the way up the optical spectrum, and comparing the template values for the wavelength with the observed on the same instrument values of the wavelength, and indeed shifts do seem to, complex distortion patterns do seem to be present. Whether or not they're going to, that work is being written up at the moment by Jonathan Whitmore at Swinburne. Whether or not those patterns will explain this, unfortunately I don't think we're actually going to know, because all that we can say about those distortions is that they apply to the instrument at the time at which the asteroid measurements were made, but we don't know that they apply to the instrument at the time at which the quasar measurements were made, and we do know that they're time dependent. So this is very cruel, but there's not really very much we can do about it. But there's a lot of work going on right now to try and understand these problems. I may have painted a picture which sounds as if this is so complicated, forget it, go away and do something else, but I don't believe it is like that. I think that there's been so much work done now that we have a pretty good understanding of these data, and that is improving all the time. There are some other ways of getting handles on variation of alpha using astrophysical data, and I'll come back to those methods in the next talk. Thank you.